Are you using a real-time operating system? Are you confident that you understand what's going on in the runtime world? With Tracealyzer, you can be. At Percepio, we developed the Tracealyzer tools for runtime analysis. Today, we introduce a new generation tools, Tracealyzer 3.0, and today I'm going to demonstrate this, how to do continuous trace on free RTOS with a standard J-Link debug probe.
I'm going to talk a little bit about Tracealyzer and give you some background about what it is, and then Johan is going to run a live demo, because Percepio, it's about perception. Tracealyzer is about seeing the whole problem, and we can't just show you slides and talk about it, so you have to actually see what we're doing. As you all know, I mean, software is all about timing. In any kind of real-time system, it's all about timing. There's a lot of stuff going on and a lot of stuff coming in, but you always need something to order it, because the CPU only does one thing at a time. More often than not, that's an RTOS in the background, right? When you're looking at the code, if you're just looking at straight code, you're like the blind guys looking at the elephant. You've got one view. There it is. I've got code. But in a real-time system, you've got an elephant, and it's in 3 dimensions, and there's timing factors coming in, and there's all kinds of stuff coming in around it. What we do with the Tracealyzer is we have an instrumented core, or an instrumented kernel, and we're pumping stuff out some channel, and we'll be able to look at the entire system here. The nice thing about it is, as it says here, is it's software debugging, so it's software defined, as I said, an instrumented kernel, and no extra hardware is required. What you get out of this is trace information with 20 separate views, and they're all interconnected. We've got user views, we've got event graphs, we've got CPU load graphs, all kinds of event charts. This is our main window. It's all about debugging, validation, profiling, training, and documentation. I mean, if you're debugging in RTOS, how do you actually see what's going on while your system is running? Well, we can show you. Validation, is my code actually running like I intend it to? You don't really know that until you see it as it comes out. RAM and CPU usage per task. Training, how do you get your new guy up and running on your system? How do you show them what's going on? And then documentation, how do you show other people what you've done and what kinds of changes you made? What we're actually talking about today is what we call Tracealyzer 3.0. Until now, what we've been doing is there's basically 2 ways of capturing trace data from an operating system. You can write it into a RAM buffer, initialize a start event, fill up a RAM buffer, and then download it. And so you get a couple of seconds as sort of a snapshot of your elephant, if you will. The other way is to run it as a RAM buffer and just continually fill a RAM buffer and wait for it to stop. Boom. So you convert it into sort of a software black box. So you get the last few seconds of whatever it is you're running. And then you can look at it in all kinds of detail. Now, this is, what we're talking about is streaming trace, and we're going to stream that over the J-Links or TCP or other channels. So what we're talking about here is streaming the trace out continuously, and we're talking about very long traces, 20 minutes, arbitrarily long traces. And this gives you massive amounts of trace data. So what we've got is conceptually is a way to look at your elephant in 3D from all kinds of angles. So I'm going to show you just a couple of the screens on Tracealyzer. This is our main screen. What's interesting here is a vertical timeline. This is rather unique in the debugging world. So we have all of our timelines here, and then what they are over here. There are other tools that do this, but their timelines are on the horizontal, and you don't have a clear sense of what's going on here. This view here is, as I said, the main view, and you can zoom out or zoom in, essentially out to full scale or into a very detailed view. This is our communications flow graph, and when I mentioned validation earlier, if you're writing a real-time system, typically you create a communications flow graph at the design level on paper somewhere. So that while you're designing, you understand what's going on. Well, this is actually created from the data in your trace. So this is created in not in real time, but as a post-analysis phase. So we analyze the data that's collected in your trace and construct these graphs so that you can see actually what is going on. And does this really match what what my design said it should do? CPU load graphs, so we can see each interrupt service routine, each kernel call, etc., how long everything is taking, and what our CPU load is for each event. And then a user event plot. We can also instrument, as I said, we instrument the kernel, but we can actually add user events, and in this case it's a sine wave, just so you can see what's going on. So this is the kind of thing that Tracealyzer can do on a very concrete level. And now Johan's going to show you a couple of situations where where our customers have actually found bugs and found different RTOS-related timing issues using the Tracealyzer.
Okay, so for this demo, I'm using this little development board from Atmel. It's a Cortex M4 MCU with an integrated, very low-cost Sega J-Link debugger here, this chip. And what we'll do now is, this has a pre-programmed application, a demo application, and it also includes our trace recorder. It's a little piece of software that hooks into FreeRTOS in this case, and intercepts various function calls, API calls in the operating system, and scheduling events, and also application events, and then channels them out using the J-Link. And we use Tracealyzer to receive and visualize it. So now I'm going to start with just demonstrating how to make a trace. It's really simple. All you need to do to configure this, once you have the recorder library hooked into your application, all you need to do in Tracealyzer is to set your chip, basically. I select Connect to Target System, awaiting data, it says. If I now click Start Recording, it will set toggle a variable in our recorder library and start collecting data. And now we get a view like this, a live view showing the CPU usage of all the application tasks and any instrumented interrupts in the application. This is mainly to get a sense of what's going on in real time. And then we have the full, when you stop this, you get a file that you can store and visualize. And here you see the amount of data we record. It's about 100 kilobytes per second at the moment. That would translate into a few hundred megabytes an hour. So it's quite manageable amount of data. If you have a 1 terabyte flash drive, I mean, you can store days or weeks of trace in this way. This is not function level trace. It's not instruction level trace like you get with ETM or ETB from the processor. This is software-defined trace, meaning that we have instrumentation that records selected points in the system. We have a pre-packaged instrumentation layer for FreeRTOS and other supported operating systems, which you just include as a header file, very simple. So you don't need to do all this instrumentation yourself. Okay, now we have recorded for a while, and then we simply click View Trace. So now we get this visualization that Mike showed before. This is our standard demo application showing a lot of tasks, sending messages back and forth. I will just demonstrate this, the different views quickly, how they look live, and then I will go into one or two use cases where we have stories from customers with real problems. As Mike mentioned, we have this main view with task scheduling interrupts. This can be shown in different ways. We call them view modes. You can easily switch with these buttons. This is the Gantt mode, where you have one column for each interrupt or task. But if you have a lot of tasks, you can use this mode instead, where you get a kind of stacked view. And then you see the spikes here, where you have a lot of tasks being activated at the same time. So if you zoom out a lot, these spikes will still be very clear. Now we are looking at several seconds of execution here, and we can still see these relevant spots where the intensity is higher. And this view is complemented by several other views. But first I would like to show you also all these annotations that we can see. For instance, things like, here we see operating system ticks, for instance, but we can also see calls to the free RTOS kernel or any RTOS kernel, sending and receiving of messages, memory allocation, etc. And you see also that things are color-coded, so you can see that here we have a timeout. This red one means that there's blocking, etc. And also user events, that is application logging calls. The developer has added a call to his application to log this value here, and then we can visualize this data in plots, etc. And this main view is complemented by several other views, with this one, for instance, showing CPU usage. Here we have very kind of boring behavior, quite stable, good. And then you can add other views to this timeline, like this application plot. Now we have 90 seconds here. You zoom in a bit, you see a bit more details, and so on. And the great thing with this, as Mike mentioned, the elephant, we have this, there's a huge amount of patterns and dependencies in this data. And if you just look at it from one perspective, you see one thing, or you see certain things. If you can kind of twist and turn this data, you see new things. Since all these data points are interconnected, if you click on a data point here, the corresponding thing here in the main view is highlighted, like that one. So now we know that if this particular point would be an anomaly, we could see exactly where in the trace that occurred. It could be, for instance, occurrences of some interrupts that disturb the execution. But let's look at some more interesting cases. Here we have, let's begin with this one. In this case, the developer or our user had a periodic activity, a periodic task that was supposed to run at every 5 milliseconds. But they noticed in their output that they had some jitter. There were some variations in this 5 milliseconds. Sometimes it wasn't 5 milliseconds, it was 6 or 7 milliseconds. And why? They had a simple delay in their in a loop. This was no complicated code. So they looked in Tracealyzer. Here we can see the time between activations of a task. Here we have 3 different application tasks. And if we filter this a bit, we can see this particular one in more detail. And here we see that we have a quite steady behavior, 5 millisecond inter-arrival time of this task. But here we have 6.5 milliseconds all of a sudden. Why is that? Now if we click on this data point, we focus the view here, and when we have anomalies like this, one could suspect that it has to do with the operating system scheduling. So let's enable this annotation of operating system ticks. And if we zoom in a bit more here, and I mean what this means is that the operating system interrupt is generating an event every time it executes. It should be every millisecond in this case. But here we see a gap. There isn't an event here for over 2 milliseconds. Why is that? If we add more information here, things that have been recorded, we see that we see this logging thing that it's updating some file at that point. And so it's probably some sort of critical section related to the file system. And when they looked further, they realized that they were actually disabling interrupts to do this, to implement this critical section. And this interrupt disabling, I mean, it worked, but it also disabled the scheduling. So therefore this task was delayed, even though it had nothing to do with this particular critical section. So it was kind of a stupid mistake that was discovered this way. So when they changed this behavior and instead used the mutex to implement this critical section, that way they could implement a lock that only affected the tasks that used this resource, and then they got a trace like this instead. And here we see now that there are mutex events, give and take mutex, and if we look at the time between activations of this sampler task, it's now perfectly stable at 5 milliseconds. I have one more example I would like to show you. In this case, they noticed that the system got random resets, and they suspected that this was due to a watchdog. But they didn't really understand why this happened. So they instrumented the watchdog events with these user events, so they could see the remaining time on the watchdog every time it was kicked. And we see here that there is a margin here of 10 milliseconds every time. And but then in the end of the trace, when we get this reset, we see that the margin drops. And in the end, we have this system reset as the watchdog fires. And we can actually see this using this user signal plot as well. So here we have plotted the margin on the watchdog. And we see it's typically at 10 milliseconds, but here we get less and less margin and in the end. If we correlate this with the CPU load of the system, we see here that this bright green thing, a task called server task, executes a lot in this area. And it turns out that this server task is triggered by incoming network messages. So it runs kind of randomly depending on the amount of stimuli. And the dark green task called control task is not getting enough CPU time. And when looking further into the system, it turns out that if we look at the communication flow graph here, we see that this very high priority task, sampler task, communicates with the control task through a queue. And when this task is not getting enough CPU time, it can't read the messages fast enough. So this queue becomes full, and then this task is actually blocked. This is an example of priority inversion, actually. A low priority task is blocking a high priority task. So what can we do to change this? Well, they realized that we could actually change the priorities here of these two tasks. And when they do this, we get a result like this. And looking at the CPU load graph now, we have a much more stable shape here of this high priority task is getting 20% all the time. And now control task is the middle priority task and gets also a fairly even amount of CPU time. And we don't get these resets. If we add this margin on the watchdog, we see it's a line now, no anomalies. And the great thing with the new Tracealyzer version 3.0 is we have the support for continuous trace. continuous streaming of trace on a standard JLink debugger. So we can do, instead of a few seconds of trace, limited by the amount of RAM in the chip, we can trace for many minutes or even hours and hours. At the moment, we're limited to, in practice, to somewhere between 10 to 30 minutes, depending on the power and the amount of RAM in your computer, because currently we can only load the whole trace at once. We don't have any means to kind of search and filter the trace at the moment, but that will come in the next major release, 3.1. But we can still record basically for how long time, I mean, for any amount of, in practice, unlimited time, as long as you have disk space. As soon as we have this capability of scanning a huge trace and finding, taking out the right chunk, so to say, and load it, you can work with traces of measuring hours and hours.
Traditionally, this has only been possible with fairly heavy-duty JTAGs with a separate ICE connector, so a separate trace connector, and actually implementing trace coming out of the chip itself. The majority of Cortex and ARM parts don't actually have the trace module on them, and it is essential to have trace. So this lets you trace on almost every Cortex and ARM part there is with a standard JTAG, as opposed to having to have pins and the larger version of the chip with the trace on it, the trace module on it.
And the streaming is actually not just for ARM. We have support for the JLink streaming supports the Renesas RX series as well. And we also have a kind of custom, you can customize the streaming to use TCP/IP if you like. So you can send the trace over a network connection from basically any 32-bit chip. And you can also channel the trace to a memory card or any custom channel you might have, as long as you have a way of kind of transferring the file to a host computer.